Parameterized models play a central role in machine learning by relying on continuous optimization methods to learn from data. These models, particularly neural networks, extend simple learning approaches by enabling the modeling of complex relationships through trainable parameters. While simple models often allow loss functions to be expressed in closed form, neural networks, especially deep ones, produce highly expressive but analytically complex loss landscapes. Their ability to learn rich structures improves significantly as the amount of available data increases, though simpler architectures may be more suitable when data is limited. Foundational machine learning model designs include least squares, regression, and classification methods, which establish core principles for supervised learning. Neural architectures evolve from the perceptron model by incorporating activation functions and more flexible loss functions. Typical architectures consist of an input layer, one or more hidden or bottleneck layers, and an output layer, with learning driven by minimizing reconstruction or prediction error, often measured as squared differences. Matrix factorization emerges as a key concept in unsupervised learning, supporting dimensionality reduction, clustering, and predictive modeling in recommender systems. Neural approaches to binary and multi-class classification include techniques such as the perceptron, Woodrow-Hoff learning, logistic regression, support vector machines, and their multi-class extensions. These methods illustrate how neural models generalize traditional algorithms while providing increased modeling flexibility. Autoencoders form a foundational neural architecture for unsupervised learning. They aim to reconstruct input data by learning compact latent representations, optimizing parameters to minimize reconstruction error. Single-layer autoencoders are closely related to singular value decomposition, SVD, sharing identical loss functions in unconstrained settings. Logistic matrix factorization extends this concept to binary data, making it particularly effective for recommender systems with implicit feedback. Deep neural networks offer substantial representational power by learning hierarchical feature abstractions. Deep autoencoders enable nonlinear dimensionality reduction, mapping complex data manifolds into low-dimensional spaces. These models can achieve highly compact representations and, in some cases, serve as alternatives to visualization techniques such as TSNE. Applications include outlier detection, clustering enhancement, feature selection, and multimodal embeddings, where heterogeneous data sources are mapped into a shared latent space. In recommender systems, neural architecture adapt matrix factorization principles to sparse, element-wise learning scenarios. Rather than processing fully specified matrices, these systems learn from individual user-item interactions. Loss functions are modified to account for missing values, focusing optimization only on observed data. Neural networks are also widely used to learn word embeddings from text. Two main strategies are employed: factorization of word context matrices and predictive neural models. The Word2Vec framework includes the continuous bag of words CBOW model, which predicts a target word from surrounding context words, and the skipgram model, which predicts context words from a single target word. Skipgram performs particularly well with rare words and large datasets, despite higher computational cost. An important optimization of skipgram is negative sampling, which replaces full softmax computation with sigmoid-based binary classification. This approach efficiently incorporates both observed and unobserved word context pairs during training. Similar sampling-based neural architectures are applied in social networks, where edges may represent binary or weighted relationships. Mini-batch sampling and stochastic gradient descent are commonly used to improve scalability and performance. Deep learning models introduce significant computational and optimization challenges, which become more pronounced as network depth increases. Training neural networks requires solving complex multivariable optimization problems, where parameters correspond to connection weights across multiple layers. In very deep architectures, managing gradient behavior across layers becomes particularly difficult, leading to instability during training. A core challenge arises from the nature of gradients. They describe rates of change over infinitesimally small intervals, while optimization algorithms must take finite steps. Selecting an appropriate step size is critical. Very small steps result in slow convergence, whereas excessively large steps can cause erratic behavior or divergence due to abrupt changes in the optimization landscape. These issues are amplified by the highly non-convex loss surfaces of deep networks and are further exacerbated by poor initialization choices or improper input feature normalization. As a result, the straightforward steepest descent direction often fails to support meaningful progress when larger steps are taken. Despite these difficulties, many optimization challenges in deep learning can be mitigated through appropriate algorithmic and architectural choices. Increasing network depth offers representational advantages, but it also introduces common training problems such as vanishing or exploding gradients, sensitivity to initialization, and convergence to suboptimal solutions. Addressing these challenges requires a careful understanding of gradient dynamics, local minima, and architectures designed to be more depth-friendly. Various optimization strategies are employed to stabilize and accelerate training. Gradient descent remains fundamental, but enhancements such as momentum-based methods improve convergence by smoothing updates over time. Second-order optimization techniques, including the Newton method, provide faster convergence by incorporating curvature information, though they are computationally expensive. Practical approximations to Newton's method and conjugate gradient techniques offer more scalable alternatives suitable for large models. Batch normalization is a key technique for improving training stability by reducing internal covariate shift and enabling the use of larger learning rates. Additional implementation strategies focus on accelerating computation and reducing memory usage through model compression and efficient execution techniques. Neural networks are also shown to unify many traditional machine learning models. Several classical methods, including singular value decomposition, can be interpreted as simplified neural models, producing nearly identical results when expressed in neural form. However, neural networks surpass traditional approaches by naturally extending into nonlinear models, making it easier to explore richer representations and adaptations. Both shallow and deep neural models find practical applications across supervised and unsupervised learning tasks, including recommender systems, text embeddings, and graph embeddings. Effective hierarchical feature engineering is essential in these contexts, but success depends on overcoming training challenges through a solid understanding of optimization behavior, architectural design, and acceleration techniques.